Hi, everybody. So this is worksheet 2 on electric potential. Before we get started, I'd like it if you could scan in just some announcements. This is going to be like the second recording of the other one that's already on the YouTube playlist. Going forward, our Tuesday session is going to be in person, Wednesday virtual and recorded, and then that Friday 8 a.m. to 9 a.m. Q&A, homework review, exam review question is going to always be in person also. So stay tuned for that. Again, please sign in. I know it's so annoying if you're watching the recording, but if you could do it a few times this semester, that'd be great. And before we get started, I just kind of want to like clear up some things from last time and then lay a foundation for this worksheet. So just like with our electric forces, just be mindful that we're using little q and then how they interact, wherein plus will always like be attracted towards minus, and how, you know, two positives will push away from one another. Next thing we're looking at here is, you know, potential from high to low. It's always conservative. That should be as expected. And then electric potential energy. Similar effect as the electric force. Here we have from high to low potential. And obviously as it gets closer here, the potential energy decreases. And we're going to go over application of these equations. But some of these should bring familiar from last time. And then here's just a work equation, but they use U. I like to write W. Okay. And then just some terminology. It's pretty subtle, but it is a very important distinction. That being electric potential energy versus electric potential. So electric potential energy refers to a charge, versus electric potential refers to a position. So like if it's asked like what's the electric potential at this position, or what is the electric potential, I don't know, like 2 meters away, that means we're discussing this, right? Unless if there's a charge there, we're using these conditions. Again, here's just a way to visualize that potential energy in different systems. Here's like a negative charge and a plus, yeah, okay. And here are our equations. Let's just start with this potential energy equation. You know, delta PE equals Q, that final minus initial, or just delta V. Here's our electric potential equation. And here's an alternate way of expression. I just want to note that like what the different Q's mean that you will see. So big Q is the charge that creates the potential, and little q is what experiences the potential. So like keep that in mind like when you're working with something like this. Like this little guy is little q, and it's going to be what's experiencing the potential energy, electric potential energy from this big Q. All right, and then obviously voltage is electric potential difference. This is a unique equation per the specific terminology, constant electric field between two parallel plates. So within that condition, it's one you're going to see often. We did it. Sorry, helicopter going over. It's similar to an example we did today in class, or yeah, today in class, unless you have Thursday class. So just keep this in mind when you see constant electric field between two parallel plates. That means you can apply this equation, and we'll do that later on. And then finally, you know, work. Okay. So just gonna move it along. These equations should be kind of review now. And then there's just some things I really want to get clear. A student asked me about it after class, and I realized like it's a very important distinction to make. So voltage is the amount of energy required to move a unit between 2 points. So like from here, that'll be like VA minus VB. And then potential is the difference between the higher potential of one point and the lower potential of another point. So remember, potential high is always on the plus side and it goes towards low. It kind of matches up with the electric field. So let's just look at this first example. You know, you guys can just like look at all of them right now, but I'm just going to be talking about here. So when we're first talking about voltage, it's the amount of energy required to move a unit charge between 2 points. So that's between A and B, right? So that's how much energy is needed. That's what this part is telling us. Here, this is potential, and this is the difference between the higher potential of one point and the lower potential of another point. So this is where the higher is minus the lower that's right here. And that's how it comes up to be this. Normally our test charge is going to be a plus. So like I would say like these are less common, but it's just important to keep in mind like that the higher potential energy is always going to be associated here because, you know, the plus is going to go towards the minus. And then look at our instances of work here, right? How the sign matches what you would expect, right? You would expect this plus to go towards the minus, but then when you're going against that, you know, it's going to come out as negative. And difference in potential equals a difference in voltage, and that's just by definition. So just keep these two things in mind as we go forward. Other than that, this stuff should be pretty clear as we've had the opportunity to do a homework on this and whatnot. So I think that explaining the theory can sometimes get confusing, and the terminology, we just get, you know, in the trenches of the terminology. Just seeing it applied is way easier. So I'm just going to do that. So let's just discuss this number one. Obviously, potentials is a scalar, so we have to recognize that minus or plus. It's not a vector. All right, so let's just talk about number one. We have 3 point charges arranged at the corners of a square as shown. All sides are L distance. What is the potential at the fourth corner? I'm just going to delete that square. Fourth corner, point A. So, you know, distance L, distance L, distance L. You get the picture. I call this one Q1, Q2, Q3, where Q1 equals 3Q, Q2 equals Q, and then Q3 equals minus 2Q. So we have to express all this, and this is an equation we saw on the first page. Remember, V equals KQ over R. So I just wrap the back factor out the K because it's a constant for each one of these values, and then, you know, I label everything with my respective R values. At this point, I can plug in. As we discussed, I defined Q1 as Q3. I defined Q1 as equal to 3Q. That's this position. Q2 is this position, just Q. And then Q3 is this minus 2Q. So I made sure to include that minus here because, again, potential is a scalar. All right, and then all of these R values, you know, it's L, L for 3 to A and 1 to A. And then for 2 to A, just some quick Pythag. We know we're dealing with a square as L root 2. At this point, we can factor out the Q and the L. That's just arithmetic right there. And then express. And this is what you're going to come out with as your answer. Cool. This one's pretty, just to get our, you know, dip our toes in the electric potential pool. All right. Wait a few seconds. Any questions come in? Okay, let's move on. So this one also is very quick. It's just to, like, you know, it's a proton in this case, and we want to talk about like work and whatnot. So how much work does the electric field do in moving a proton from a point at a potential of 125 to a point at minus 45 volts? So what's our equation? You know, it's work negative potential. We express like this. Here is where we are. Here's where we're starting from, you know, final minus initial, and here's where we end. I just call it VB. Charge of proton, don't forget this negative right here. These negatives end up canceling out. And then it's just, again, simple multiplication right there. Okay, so I think that we have kind of a good foundation to approach the next two questions. And this is it's gonna get a little bit more involved here. Let me zoom in. Oh, also apologies, I'm doing this PowerPoint way again, but when we go back in person, I will have a better way to do it for everybody. Okay. I am sharing my, yeah, okay. So it says, what is the change in potential energy when a -2 microcoulomb charge is moved from point A to point B, which are 16 centimeters apart? What is the change in potential energy if the charge is then moved from B to infinitely far away? So here's our drawing. I'm just going to delete this also. Here's our drawing we're given. I kind of just expanded it right here, and I'm just going to explain everything that we have. So first is, here's our position A. This is where the charge is originally, that being the -2 microcoulomb charge. And then 12.12 meters to the left is this plus 38 microcoulomb, and then 0.24 is this 38 microcoulomb. And we want to know when it's moved from point A to B, what is the change in potential energy? So we know we're looking for some delta PE, right? And that being a delta V, because we already explained that we're looking for the amount of energy required to move a unit between 2 points, and then we're going to plug that in to find potential difference, right? So that's what's represented there. So the first thing we can do is find VA, because this is pretty simple. We know almost everything here. Firstly, we have our, I'm going to use this equation here. So VA is made up of these two charges are acting to induce that electric potential at this point, right? So we have K, which is a constant, Q1 over R1, and then we have K, Q2 over R2. We can just factor out the K and the Q because they're equal to each other. And then we're just left with these fractions, which is just 1 over their distance, right? And right there. At this point, we can just multiply and we get this. So now we have a voltage when it's here. So next, we have to just do some Pythag to be able to get these values, that being R3 and R4, because everything else stays the same except for the distance away it is from the charge. So now that we have these values, very similar to how we did it up here, we're just going to factor out the K and the Q. The reason why we can factor out K and the Q is because in this case, they're equal. Sometimes though, you'll have to keep them in and maybe you can only factor out the K, or you can factor out the K over R. It depends on what's what's equal and what's not. But in this case, K is constant, so it's always going to be equal, but the Q's are also equal. So we can factor out the K and the Q. 1 over R3, we just found that. 1 over R4, that's right here. We just plug in and multiply. We now have enough to do our change of potential equation. We have our charge, that's given in the question. We have our VB value, excuse me. Yes, we have our VB value and we have our VA value, so that's final minus initial. And then we'll come up with how much energy is required to move from point A to point B. All right. So the next thing it asks is, let's say we move it from B to infinity. So let's first find that voltage at that potential at infinity. So what we have here is, K Q1 over infinity and K Q2 over infinity. Because now you can imagine this guy is like all the way up. And that new radius is infinity. So anything over infinity equals 0. So when we plug back into our equation, Q, V final minus V initial, this guy pops out to 0. So it's left with is just VB, which we already solved for before, right over here. Don't forget that that's negative because this minus sign. Those guys cancel out and we'll come out with a positive. Okay. And then I want to just be very clear on this. I said difference in potential equals the difference in voltage. So remember that is true. So back when I was describing, I think it was this point, I said potential, but we can consider those the same thing because the difference in potential equals the difference in voltage. Okay. See if there's any questions on this one. All right, I'll just move it along then. Yeah, this is going a lot faster because I don't need to write anything. So I guess it's good because you guys get it's a shorter video. But let's just move on to number 4. So here's kind of that constant electric field parallel plates situation we're talking about where this equation comes into play. So let me just zoom in. So after an electron is accelerated from rest by a potential difference of 2,200 volts, it passes between 2 parallel plates that are 6.5 centimeters long and 1.3 centimeters apart. The parallel plates have a potential difference of 250 volts. At what angle will the electron be moving after it passes through the plates? So I first drew it like this. This is kind of how we traditionally envision it, higher potential, lower potential, but we know it's moving this way through the parallel plates. So looking at it vertically is kind of confusing. So flipping it horizontally is more reasonable. And then if we want to do it even, if visualizing like this is too much still, we can even do it like this, informing us that we need an X and Y component. So let's first just recall that the potential energy equals kinetic energy. So we have a potential, we've defined potential energy in the case of these electric systems. And we already know what this is from 135A. We're just going to simplify replace this ED by delta V. That's an equation swap we can do. We showed that over here. So working with this kind of equation. And we're left with, we want to solve for this velocity value. Okay. So we just, multiply by 2, divide by m, square root, we'll get this expression. We solve for velocity. We know that for delta V, it starts at rest, and then the final position is 2,200. So I just plug in 2,200. Clean this up, and you have a velocity. We also know there's no acceleration in the x direction. So v naught x equals the v final x, that being velocity. And that's just, no acceleration, right? So next we're going to look at the y direction. So with the y direction, we just use this kinematic equation. We have to solve for acceleration and time because we don't know any of that information yet. So first, let's use our forces. F equals ma. We want to solve for a on one side, where the force equals the EQ, where E equals V over D. So again, that was a callback to that equation I said we could use. So what does that tell us? That equals VQ over the distance divided by M, that being the vertical distance, because we're talking about the Y component right now. So next is time. That's a change in X over velocity. We now know, based on what they gave us in the problem, we know what the change in X is, and we have a velocity, so we can solve for the amount of time that it takes to do that. So here we can use what we learned in 4 and 5, plug it into our equation here. V naught Y equals 0 because, it's initially going just in the X direction. So we're left with AT. We plug in what we solve for right here, and we get this expression right here, at which point we just need to plug in our whole values and solve. So now we have the Y final component of its speed, the Y component of velocity. At this point, we can just set up a triangle, do some trig here, and tan theta, that's the Y component over the X component, inverse tan, and then we get some angle above 15.9 above the X axis, right? So that's that right there. So I'm going to zoom out. Let me first ask, are there any questions on this one? Okay, I'm gonna then pause or end the recording and then open it to homework questions, and then questions may be on this sheet that in case people didn't want to speak out for the recording. So thanks for watching. Make sure you use that QR code to sign in case you didn't. Thanks, guys. So.